What you have just witnessed is pure vorticity chaos turned into a so-called Lambosine vortex. Yet, this black hole behavior is not observed in our physical space, where chaos remains chaos, as the current simulation shows. How is it possible? Welcome to a trip into the land of self-similarity. The Lambosine vortex is an incompressible, non-steady Newtonian flow disposing of a rotational symmetry for the velocity field with an initial circulation. Navier-Stokes equations are numerically solved with the physical parameters and boundary conditions listed and initialized with an almost Dirac vorticity profile. As can be seen, the vortex diffuses over time into the domain due to viscosity, with a clear decrease in vorticity represented by the black profile and the vertical component of velocity on the right-hand side. Remarkably, the structure of the curves appears to be the same throughout the simulation. One can expect a so-called self-cinema solution, that is to say a stationary solution in a particular rescale space, thanks to the study of scale invariances throughout the physical problem. And here is the correct scaling factors analytically determined. All velocity profiles obtained for different times are superimposed on a red dashed master curve, perfectly known theoretically. It means that in this new self-similar space, the problem has totally become stationary compared with the insert recalling the physical one. But this is just a rescaling step obtained with results of the simulation in the physical domain and explains why do we have cut curves. The size of the box is divided with a scaling factor that increases with time. Therefore, to overcome this numerical problem that would need bigger domains for longer times of simulation, we need to compute directly in the self-similar space. To do so, one needs to use the self-similar variables of the Lambosine problem and the definitions of the self-similar velocity and pressure found theoretically, and to inject them into the native Navier-Stokes equations in order to get the self-similar ones. The two major changes are the definition of a new advection velocity lambda along with a new term source on the right-hand part of the equation. By solving these transformed equations, we zoom out to the right speed of the vorticity field to make stationary what was initially chaos, as evidenced by the velocity profile that inevitably converged to the time-independent analytical solution. Deviations remain, however, due to 2D Cartesian modeling for an axisymmetry problem.